Something is amiss in our comprehension of the cosmos. Cosmology appears to be approaching a confrontation regarding one of its most fundamental inquiries. How swiftly is the universe expanding? For over a decade, two kinds of measurements have been at odds. Observations of the contemporary universe generally indicate that the rate of expansion, known as the Hubble constant, is approximately 9% quicker than forecasts based on early universe data. Researchers anticipated that the James Webb Space Telescope, the most sophisticated telescope ever constructed, would assist in resolving the matter once and for all. However, a consensus has yet to materialize. Instead, the premier observatory has solidified the discrepancy with remarkably precise new observations that threaten to overturn the standard model of cosmology. The new physics required to amend or even substitute the 40-year-old theory is now a subject of discussion. An exhilarating and intriguing possibility is that there's something we fail to grasp about the cosmos. Join us as we delve into new ultra-deep images from James Webb, which just confirmed that there is something profoundly wrong with our understanding of the universe. Our cosmos began with a bang, the Big Bang. Energy, mass, and space ignited into existence, all within a fleeting moment. Then the young cosmos was formed, an expanding, roiling plasma mixture of matter and antimatter particles that emerged into existence only to annihilate each other upon contact. Left to their own devices, the matter and antimatter within this plasma should have consumed one another entirely. Yet scientists believe that some unknown imbalance enabled a greater quantity of matter than antimatter to be produced, saving the universe from immediate self-destruction. Gravity compressed the plasma pockets, squeezing and heating the matter so that sound waves, traveling just over half the speed of light, called baryon acoustic oscillations, rippled across their surface. Meanwhile, the high-energy density of the early universe's crowded contents stretched space-time, pulling a small fraction of this matter safely from the fray. As the universe inflated like a balloon, the standard narrative asserts that ordinary matter, which interacts with light, coalesced around clumps of invisible dark matter to create the first galaxies, interconnected by a vast cosmic web. Initially, as the universe's contents dispersed, its energy density, and thus rate of expansion, decreased. But then, roughly 5 billion years ago, galaxies began to recede once again at an ever-accelerating pace. The cause was another observable and enigmatic entity known as dark energy. The simplest and most favored explanation for dark energy is that it is a cosmological constant, an inflationary energy that is uniform everywhere and at every moment, woven into the expanding fabric of spacetime. Einstein referred to it as lambda in his theory of general relativity. As our cosmos expanded, its overall matter density diminished, while the dark energy density remained constant, gradually making the latter the primary contributor to its overall expansion. Combined, the energy densities of ordinary matter, dark energy, and light energy set the upper speed limit of the universe's expansion. They are also key components in the lambda-cold dark matter (LCDM) model of cosmology, which maps the growth of the cosmos and predicts its conclusion, with matter eventually spread so thin that it experiences a heat death known as the Big Freeze. Many of the model's predictions have been shown to be remarkably accurate. But this is where the issues begin. Despite extensive searching, astronomers have no understanding of what dark matter or dark energy truly are. As Ophir Lahav, a professor of astronomy at University College London who participates in galaxy surveys of dark energy, stated, "Most people concur that the universe's current composition is 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The awkward reality is we don't comprehend the latter two. However, an even more significant threat to the LCDM model has emerged. Depending on which method astrophysicists employ, the universe seems to be growing at different rates, a disparity known as the Hubble tension. Methods that examine the early universe indicate it is expanding substantially faster than LCDM forecasts. These methods have been scrutinized and validated by countless observations. Therefore, as Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb measurement, remarked, "The only reason that I can understand at this point for them to disagree is that the model we have between them is perhaps lacking something. Measuring the universe's expansion requires more than a radar gun. The first method to assess this growth examines the so-called cosmic microwave background, CMB, a remnant of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be observed across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is nearly entirely uniform, but hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations caused it to clump as the universe expanded outward. This soap bubble structure ballooned into the cosmic web, a network of intersecting strands along whose junctions galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the quantities of regular matter and dark matter, as well as a value for the cosmological constant, or dark energy. Plugging these into the standard model produced a Hubble constant of roughly 67 kilometers per second per megaparsec. Let's pause on this figure for a moment. If a galaxy is at a distance of 1 megaparsec away from us, that means it will recede from us and we from it at 67 kilometers per second. At 20 megaparsecs, this recession increases to 1,340 kilometers per second and continues to grow exponentially from there. If a galaxy is farther than 4,175 megaparsecs away, it will retreat from us faster than the speed of light. A second method to determine this expansion rate utilizes pulsating stars called Cepheid variables, dying stars with helium gas outer layers that grow and shrink as they absorb and release the star's radiation, causing them to periodically flicker like distant signal lamps. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid was, the slower it would flicker, enabling astronomers to measure a star's absolute brightness and thereby assess its distance. It was a groundbreaking discovery that transformed Cepheids into abundant standard candles for measuring the universe's vast scale. By connecting observations of pulsating Cepheids, astronomers can construct cosmic distance ladders, with each rung taking them a step back into the past. It's one of the most accurate methods astronomers have today for measuring distances. To construct a distance ladder, astronomer Wendy Friedman stated that astronomers established the first rung by selecting nearby stars and cross-referencing their distance based on pulsating light to that determined by geometry. The subsequent rungs are added using Cepheid readings alone. Then, astronomers examine the distances of the stars and supernovae on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This provides a precise measurement of the Hubble constant. In 2019, the method was employed by Rees and his collaborators, who focused the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 kilometers per second per megaparsec when compared to the Planck measurement. However, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some leeway to argue that the result, however astonishing, could have arisen from a measurement error. When the James Webb Space Telescope was launched in December 2021, it was set to either clarify the existing discrepancy or reinforce it. With a mirror measuring 6.5 meters across, Webb's mirror is nearly 3 times larger than Hubble's, which is only 2.4 meters wide. Not only can James Webb identify objects 100 times dimmer than Hubble, but it is also considerably more sensitive in the infrared spectrum, enabling it to observe a wider array of wavelengths. By comparing Cepheid variables assessed by James Webb in the galaxy NGC 4258 with luminous-type IA supernovae, another standard candle due to their consistent absolute brightness in distant galaxies, Rees and his associates arrived at a nearly identical result, 73 kilometers per second per megaparsec. Other assessments, including one conducted by Friedman with the Hubble Space Telescope regarding the rapid brightness of the most luminous tip of the red giant star branch, and another utilizing light distorted by the gravity of massive galaxies, yielded respective results of 69.6 and 66.6 kilometers per second per megaparsec. A separate finding using light bending also produced a value of 73 kilometers per second per megaparsec. Cosmologists were left astonished as Ryan Klur, a cosmologist at the University of California, Merced, who has been working to clarify the Hubble tension, stated, "The CMB temperature is measured at a precision level of 1%, and the Cepheid distance ladder measurement is approaching 1%. Thus, a difference of 7 kilometers per second, while not significant, is exceedingly unlikely to be a random event. There is a clear issue to explain. The new result keeps the answer open-ended, splitting cosmologists into groups pursuing significantly different solutions. Following the Hubble Space Telescope findings, an official attempt to resolve the problem at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only intensified the situation, as the late Vera Rubin, who uncovered evidence for dark matter, noted at the time. Nobody wanted to relinquish their toy. All those involved were so passionate about their own results and so convinced of the accuracy of their observations and measurements that it left everyone pondering. How do I make sense of this? In February 2023, with James Webb and another independent Hubble Distance Ladder result confirming the Hubble tension, cosmologists found themselves with 3 potential explanations: measurement inaccuracies, new physics, or some combination of the two. Most of the data points toward new physics. The simplest and most prevalent hypothesis suggests that dark energy behaves differently now compared to the early universe. If dark energy was powerful at one time and then lessened, it would make the universe seem smaller when we look back to its early state, resulting in a faster observed expansion rate today. Other theories exist, such as the possibility of 2 types of dark energy, or that dark matter interacts with light. But these theories introduce complexities that cosmologists approach with caution. Without additional data, dark energy and dark matter aren't the only mysteries James Webb is helping to unravel. Upon its launch, it was designed to observe further back in time than any previous telescope. James Webb's innovative imaging technology allowed it to see galaxies formed just 300 million years after the Big Bang. However, while examining the origins of the universe, astronomers found that these early galaxies were much more massive and advanced than standard models predict. Early galaxies were expected to be filled with young, hot stars forming rapidly, but James Webb revealed that many of them were brimming with heavy elements from earlier star generations and actively developing bulging cores of supermassive black holes. The basics of cosmology. The Big Bang and early universe. The universe began roughly 13.8 billion years ago in a hot, dense condition. Shortly after the Big Bang, the universe was a hot mixture of particles where matter and antimatter destroyed each other. However, an imbalance left more matter, resulting in the universe we observe today. Expansion of the universe. Hubble's law states that the universe is expanding, and the speed at which galaxies recede from us is proportional to their distance. This rate is defined by the Hubble constant. Components of the universe. Ordinary matter makes up about 5% of the universe. Dark matter constitutes approximately 25%, invisible and interacting via gravity, while dark energy comprises around 70%, driving the accelerated expansion of the universe. Measuring the expansion. Cosmic microwave background, CMB, observed as microwave radiation. The Planck satellite mapped the CMB with high accuracy, yielding a Hubble constant of 67 kilometers per second per megaparsec. Current universe measurements. Cepheid variables and supernovae indicated a faster expansion rate of 73 kilometers per second per megaparsec. This discrepancy suggests either measurement errors or new physics. James Webb Space Telescope, JWST. Capabilities include infrared observations, greater precision and clearer images of crowded star fields, reducing measurement errors. Findings confirm Hubble tension. Potential explanations include measurement errors or new physics, such as variable dark energy or dark matter interactions. Implications for cosmology. The standard model faces challenges. The current model, LCDM, accurately describes much of the universe but struggles with the Hubble tension. The ongoing Hubble tension suggests that our understanding of cosmology may need revision. Future observations and theoretical developments will be essential in resolving this tension. Expected characteristics of primordial galaxies include young, hot stars forming rapidly. JWST observations reveal that many of these galaxies were filled with heavy elements from earlier star generations and actively developing bulging cores of supermassive black holes.